Hello everyone, thank you for joining me for this video. We will be continuing from the previous video when we talked about the logarithmic function derivatives. In essence, what we will be doing is talking about some of those various function derivatives in more detail, just to iron out some nuances that are involved. Today I'm talking about the power function, and these are examples of power function right over here. These type of functions where you have a constant to the power of x, most authors would call this a power function. For some other authors, they can flip the things around and they would say this right here is an example of a power function too. You see here there's a variable and a constant, but here you have a constant with a variable exponent. When I'm talking about power functions, I mean these to be power functions where you have a constant to the power of a variable. And you know, I looked at this in terms of its derivatives in the previous video, and I've looked at this in the exponential video, but I want to talk more about this today. If you have a function which looks like this, f of x is equal to b to the x, and you know it's very synonymous to saying y is equal to b to the x. If you use a technique of implicit differentiation, you can actually derive the derivative of this, and this is how the process would work. If y is equal to b to the power of x, and you use the property of logarithms, and you take this exponent and make it into a coefficient by bringing in the natural logs, this is what you get, x natural log b, right? This by means of the properties of natural logs. I'm not doing anything new over here that you don't know. And let's make this a little more clear in terms of the x. Now if you look at this definition over here, this function, and you do an implicit differentiation of this, you see how it's not explicitly mentioned in terms of y, but if you implicitly differentiate this, you can arrive at the derivative of this type of function. And I'm going to show you. If you do the derivative of this, this is what you'll get. You'll do derivative in terms of y, you do natural log y dy over dx, and what you're doing is basically solving for dy or dx. Bring the coefficient here first, natural log b is a coefficient, and you're doing the derivative of x. Now look over here. If you do the derivative of natural log y, if you remember the previous video, the derivative of natural logs are always 1 over that variable. You'll get a 1 over y over here, and you've seen that in the previous video, dy dx. And you'll get over here natural log b times the derivative of x, which is just a 1. But the derivative of x being 1 is meaningless. You can just write natural log b and you're good enough. Now if you come right over here and you solve for dy over dx, derivative of y in terms of derivative of x, which is the same thing as looking at this symbol over here, derivative in terms of y, you take the y on the other side. You see how y is a denominator here, you take it on the other side, you get y natural log b. But when you resubstitute what this was over here, when you resubstitute this y equals bx right over here, look what happens. The derivative in terms of y is equal to b to the power of x ln b. So here we've proven that the derivative of anything which looks like this, the derivative of anything of a power function which looks like this, is going to be exactly this, b to the power of x ln b. And you know I've said this and I've mentioned this with examples in the previous video when we talked about the derivatives of the logarithmic functions. Today I'm talking about the derivatives of power function, and this is what I'm looking at right over here. And many of the derivatives which I talked about in the previous video, the derivative schemes, you have to use implicit differentiation to derive those formulas. I haven't talked about most of those, but I've talked about one over here. In my next video, I will mention the remainder as we get a little more in deep when it comes to the natural log derivatives. My previous video, which was a logarithmic derivatives, was just like an overall general survey of those type of derivatives. Here I want to focus in this video on the power function derivatives, things which look like this, and the derivatives of functions which look like this. But I'm going to be using simple examples, and I'm going to build on each example to show you how one answer changes from the previous. So let's look at some examples when it comes to these power function derivatives, and this is the scheme we follow. In the very most basic derivative, and I'm going to be building on each example, from one example to the next I'm going to build on it. Now watch. My very first example is derivative of just 2 to the power of x, which will be easy because all you have to do is follow the scheme. My b over here represents 2. When you take the derivative of this most simple form of this power function, your answer is nothing more than natural log 2 to the power of x. That's your final answer, and it looks just like this. You can put the natural log part first, or you can put the power function first, it doesn't matter. But this right here is the most basic form. Now look what happens when I slowly increase this in terms of complexity. Look, 2 to the power of 2x. Now you could simply say we can just follow this scheme, but I'll give you like a little bit of a hint over here. When in doubt, always use the chain rule, because with the chain rule you can never go wrong. Yes, the chain rule might complicate your question in terms of adding extra steps, but you cannot go wrong with the chain rule. So my hint to you all is, when you are in doubt, you cannot be wrong with the chain rule. When we use a chain rule, if you're like wondering like what can I do over here, when all you have to recognize that this is just a simple coefficient, and you could follow this very same scheme over here, e to the power of ax, and you do the derivative of this, you know what you get. You get a e to the ax, because a simple derivative coefficient, the coefficient of this just comes over here. Imagine you substitute e for 2, all you would really have to do is bring the 2 over here, and you'd get 2 times to the power of 2x, but then don't forget this natural log which must come with it, natural log 2. You could follow this scheme and you can come up with a final answer of natural log 2. Now this is where you have to be careful. You see, look here, you've added this 2 from the coefficient of this exponent, but this is 2 to the power of 1. So these two bases with different exponents, when you're multiplying expressions with the same base but different exponents, you have to add them up. Your answer would be 2 to the power of 2x plus 1. This is just simple law of exponents. But let me go back to what I was saying. When in doubt, use a chain rule. And the chain rule effect would be this. You would say u is equal to 2x. Then f of u is equal to 2 to the power of u. And then now you can bring in the chain rule. You will have 2 to the power of u, derivative with respect to u, 2 to the power of u, and then derivative with respect to this actual substituted item, 2x. Now look over here, the derivative of 2 to the power of u must follow that scheme. You'll get 2 to the power of u, ln 2, and the derivative of 2x is just a 2. Now you're basically looking at something like over here. Bring the natural log first, bring the other 2 over here next, and these dots represent multiply. Then you have 2 to the power of u, but what did u represent? It represented 2x. Now you just have to finalize your answer. 2 to the power of 1 times 2 to the power of 2x is just basically those two multiplying bases have exponents which add. You get 2x plus 1 and you're done. I have missed a little 2 over here. This should have been natural log 2. Natural log 2, natural log 2 times 2 to the power of x plus 1. Exactly the same over here. If you cannot recognize the simplicities of this formula where the a serves as a mere coefficient, you can do this and you would follow the easy scheme. If you don't make that recognition, then when in doubt, always use the chain rule and you cannot go wrong. So look over here, I've increased the complexity. I started with this simple 2 to the power of x, then I made it 2 to the power of 2x. Now I'm going to slowly increase the complexity of these exponents and we'll see what happens. Alright, let's go here. We want to find the derivative of this 2 to the power of 2x plus 1. Now look how I've increased the complexity. Before it was 2 to the power of 2, then 2 to the power of 2x. Now I've done 2x plus 1. You see, I've slowly increased the complexity of the exponent. I've slowly made it into an expression. Now again, if you were to recognize that if you were to isolate the 2 from here, you could do x plus 1 over 2, and now you've isolated a coefficient. You could follow the easy scheme and you could bring it over here, and this is what you'd get. You get 2, you see this 2 would come over here times 2 to the power of 2x plus 1 over 2, and you still have to find the derivative of anything which looks like this. You still have to add that ln 2 because you must add an ln b with it, and if you marry all of this together, you get ln 2 times this base 2 over here. Now this 2 to the 1 must multiply and you must add it with that. You have 2x plus 1, 2x plus 1 plus this extra 1 which was generated, you get 2x plus 2. Remember, this right here is 2x plus 1. Now you're multiplying it by another 2, so therefore you have two bases multiplying, their exponents must add. You get 2x plus 1 plus this other 1, you get 2x plus 2. But like I said, when in doubt and you cannot make these recognitions, something which would make you follow this type of scheme, but you still have to add this extra natural log over here at the end, then use a chain rule. Look over here. If u is equal to 2x plus 1, then f of u must be equal to 2 to the power of u. 2 to the power of u. Now you do your derivative using the chain rule. Derivative with respect to u and derivative of that u with respect to 2x plus 1. Derivative of this is going to follow this scheme over here. You'll have ln 2 times 2 to the power of u times the derivative of this is 2, and you know derivative is just 2 but to the power of 1. Now you have to resubstitute ln 2 times 2 to the power of original 2x plus 1 times this 2 to the power of 1. When you marry these things together, you get your final answer, ln 2 times 2 to the power of 2x plus 2. This final part where is just the law of exponents kicking in. But you see, there are two different ways you can approach it. You can approach it by the isolation of this exponent coefficient and then bring the coefficient here using this scheme, or you can use a chain rule because you couldn't make that recognition and do it the more safer way. But now look how our answers are changing as our exponent or the exponent expression is changing. You see I'm gradually increasing the complexity of this. Let me show you another complexity on top of this. Now look over here. You could tackle this again in this route. You could bring this coefficient down over here, and we could do that. And you could view it as this. If you bring this coefficient down over here, you could think of it as this 2 times the derivative of this 2 to the power of x squared, and then you could proceed from there. I would just basically use the chain rule over here because of the complexities which come over here with this x squared. It doesn't look like a x, but it looks like an x squared over here. I would do a direct substitution where u is equal to 2x squared, therefore f of u must be equal to 2 to the power of u, and you'd be safer to go via this route. Now look what happens. You do derivative with respect to that u, you have 2u, and then the derivative with respect to x, you have 2x squared. Now you have to still find the derivative of this using this scheme. You get ln2 times 2 to the power of u. Find the derivative of this, which is about 4x. Now look over here. This is the interesting part over here. You can rewrite everything over here. The 4x term, you can rewrite it using bases of 2. Look, natural log 2 times 2 to the power of u times 2 square x. You see this 4 is a 2 square but x. Now you got a like term over here and a like term here. You can combine them together, but you still have to resubstitute for u. Look what you get. You get natural log 2 times 2 right here. Resubstitute the u was a 2x squared times 2 square x. Now look over here. 2 bases multiplying, therefore their exponents must add. Your final answer will be this natural log 2. I'm going to bring an x over here because this x serves as a bit of a coefficient. You can just transfer it here and now bring the base part over here. 2 to the exponent of 2x squared times 2 squared, you get 2x squared plus 2 using your simple law of exponents, and you can present a final answer. So the safer approach or the route over here is not to view it in this form over here, but rather to view it in a chain rule form, because that would be a safer route and there'd be fewer doubts which would kick into your mind as to how you approach once you come to this step, because this x squared seems a little different than this x, simple x with a coefficient of a. So when in doubt, again I'll say always use the chain rule, especially for these power function style derivatives. And you know I'm talking about power function in terms of this, a constant to the power of some variable. Let's look at this question again. If you're not able to do this by any easier route, you can never be wrong 99% of the times if you're always using the chain rule, especially for these complex type of variables. If you make a substitution, and you're seeing over here I'm gradually increasing the complexity of the exponent for these power functions. If you make the substitution u is equal to square root of 2x minus 1, you must say that f with regards the function with regards to that u must be 2 to the power of u. See 2 to the power of u, and then you bring in your chain rule. And I would see a composite function playing in twice over here, so you'll have 2 kinks in your chain rule. Look over derivative with respect to that u, you get 2 to the power of u, and the derivative of u with respect to x, you get the square root of 2x minus 1. But by separating it over here, you still have a composite function, so you must do a second substitution. And now the substitution is if v is equal to 2x minus 1, then f with regards to that v must be equal to square root of v. You see here's a composite function remaining. So we do another substitution, derivative with u respect 2 to the power of u, and then derivative of u with respect to that v, we get a root v. And then derivative of v with respect to x, you get a 2x minus 1. And again, chain rule is always safe. You can never go wrong with that. Now you do your actual substitutions and your derivatives. Derivative of 2 to the power of u will be natural log 2 times 2 to the power of u, because the derivative of a power function is always accompanied by its natural log. Just think back to the derivation I did in the very first scheme of this using the implicit differentiation. We always brought in a natural log. The derivative of root v is 1 over 2 root v, and the derivative of 2x minus 1 is just a 2. But look, this 2 can cancel out with this 2, and what do you get left with? You get a natural log 2 times 2 to the power of u over root v. Let's present the final answer, and I'm going to erase the substitution right over here. Our final answer will be this natural log 2 times 2 to the power of u, and the u substitution was right here, square root of 2x minus 1. 2x minus 1 all under that square root divided by the root of v, and you know the v substitution was the 2x minus 1. And this right here would be your final answer. Not a hard question, but slightly different than previous, because now the entire exponent here was kind of locked under an expression due to this radical sign. I'm going to present two more different types of examples, and that'll be the end for this power function derivatives. See, we're giving a little bit more importance to this power function than I did in the previous video, because it does merit some level of attention. Now look at this question. If someone told you to find the derivative of this 2 to the power of x times 2 to the power of x, and you would think that we have a product rule kicking in because we have two functions f and g. If you were not to make the connection that these are exactly the same things, you could multiply them, simplify them, and you'd get 2 to the power of 2x. And now in essence all you're doing is the derivative of 2 to the power of 2x. And this is a question which I already presented earlier in the same video. And when we did this, we had answer natural log 2 times 2 to the power of 2x plus 1. Just you can rewind back to this video, and this is a question I already presented. You could rewrite this in this form, but if supposedly you didn't make that connection, that you could have just combined this and you started doing the product rule, this is how your product rule would play out. Here's my f function, here's my g function. You'd follow the scheme of the product rule. You do the g function times the derivative of the f function plus the f function times the derivative of the g function, and you would just carry it through 2 to the power of x times derivative 2 to the power of x would be just that, natural log 2 times 2 to the power of x plus exactly the same thing. You see, exactly the same thing. In essence, you could multiply all of this by 2 because you're just doubling it because of this plus sign, and you have the same things on either sides, and you could do that. Now look how your answer kicks in over here. You have natural log 2, you can keep over here. 2 to the power of x times 2 to the power of x gives you what? 2 to the power of 2x, because these items here have the same base. When you're multiplying, the exponents must add. X plus x is a 2x. But when you multiply everything here by the 2, and this is not a distributive property because everything is times over here. 2 will multiply with this entire expression only once. It's not going to multiply individually with this, with that, none of that. But this here is a 2 to the power of 1. When you multiply 2 to the power of 1 with this, the same bases, the exponents will add, and you get that plus 1 over here, and you'll still make the same connection as you did over here, and you'd still have the same answer. Alright, so keep in mind, when you're dealing with these power functions, you can have terms with the same bases, and you may have to take things an extra step using the law of exponents by marrying together those items and bringing the exponents together using the law of exponents. You don't want to present this as your final answer, that you did this 2 times ln 2 times 2 to the power of 2x, because you didn't open this up and you could have brought this and this together. You don't want to say that this right here is your final answer, because you're still one step away from the final answer, because you do have a common term here. You have two similar bases just having different exponents, but you can deal with that using the law of exponents. This right over here is the best answer. Last question. If you're asked to find the derivative of this 2 to the power of minus x, not a hard question. You can view this in several ways. You can view it as if you're looking at this where e is replaced by the 2. Remember, if you're looking at e to the power of minus ax, you can bring this minus and the a with it, and you can get minus a e to the minus ax, and you end up with your final derivative and you're done. You can view it in exactly the same way and watch, except you cannot forget that when you're dealing with a power function, you must still add the natural log. If we add the natural log like we're supposed to, and then we do the minus technique, this is what we get, minus 2 to the power of minus x, because all I'm doing is this minus 1, I'm bringing it over here. My final answer is minus natural log. I'm just bringing the minus as a coefficient right over here, and then I'm still writing 2 to the power of minus x, and I say that's my final answer and I'm done. And you would be right. You would be even right if you took this one step further and you wrote this as 2 to the power of x, because the minus exponent meant a reciprocal of that. You would be right doing that as well. So if you could not have made this earlier recognition and followed this route, and you are having these doubts in your mind and you want to use a chain rule, there's nothing wrong with using the chain rule, because that's a theme in this video. When in doubt, use chain rule, especially for these types of expressions or exponents or whatever they may be, composite items which are just out of the ordinary or which you cannot easily handle with. And you can do a chain rule by using a substitution, u is equal to minus x. Then you do f the function in regards to that, you get 2 to the power of u. Now you can just do the basic chain rule technique. Derivative with respect to u, you have 2 to the power of u, and then the du with respect to dx is a minus x. And you know this is x to the power of 1. So when you do the derivatives of this, what are you going to get? 2 to the power of u is going to follow this scheme, except instead of b's we're seeing 2's. You'll get 2 to the power of u times natural log 2, and the derivative of minus x is just going to be a minus 1, because as this 1 multiplies over here, the exponent is reduced by 1, you get 0. You get x to the power of 0, but you have a minus 1. Minus x to the power of 0 gives you a minus 1. When you do your substitution here for the u, and you write the natural log 2 first, you can write 2 to the power of u, and u represented minus x, and you have a minus over here, because this minus 1 can transfer right over here at the very beginning as a coefficient minus 1. You can write your final answer as a minus natural log 2 divided by 2 to the power of x, because this 2 to the power of minus x is the same thing as 1 over 2 to the power of x. And you have a similar answer over here as you did over here. And you're done. And this question is done. So pretty much keep in mind, I talked about the derivative of this using the implicit differentiation. And I've shown you how this type of scheme can play into these type of questions if you can view b as e. But don't forget that in the end, if you're following this scheme, you must still add the natural log. When in doubt, always use a chain rule. If you cannot make these type of recognitions, you're never wrong when you're using the chain rule. It's a safe technique. It might be a little bit more work, but it's definitely safe. 99% of the times, it's probably the best technique to use. So in the next video, I'm going to be talking about some of the enhanced items or the enhanced explanations for the other logarithmic derivatives, and I'm going to be talking about some derivations of those derivatives using the implicit differentiation. So please stay tuned for the videos which are coming up soon. I thank you for watching. Have a nice day.